Good afternoon, everyone. My name is Yavuz, and I'm a PhD student at Boston University. Today, I'll be talking about verifying differential privacy in TLA+ using a technique called self-products. The goal is to bring rigorous and machine-verifiable privacy proofs into the TLA+ ecosystem, and we have achieved this by adapting a 2014 result by Barth and colleagues. And I'll first start with some motivation. Imagine a hospital that wants to release some statistics about its patients, say the average age or the prevalence of a certain disease. These statistics can be valuable for medical research, public health planning, and all sorts of legitimate purposes. But the hospital also has an obligation to its patients. Whatever it releases should not reveal if any particular individual was a patient or not. And you might be thinking that this is easy. You just remove the names, right? Or only release aggregates instead of individual records. Unfortunately, neither of these work. Removing names is famously insufficient, and there's a long history of de-anonymization attacks where auxiliary information from another data set is just enough to re-identify people easily. And releasing exact aggregates is also dangerous. If I know the average age of patients on Monday and the average age on Tuesday, and if I know that one new patient was admitted between them, I can compute that patient's specific age. Such attacks are known as differencing attacks. Differential privacy, introduced by Cynthia Dwork and colleagues in 2006, gives us a way out. It's a mathematical definition with rigorous guarantees that hold against arbitrary adversaries. Let me show you the definition. We have a randomized algorithm M that takes an input D, and you can think of D as something like a database, and produces some randomized output. We say that M is epsilon differentially private with respect to an adjacency relation phi if, for any two inputs D and D prime that are related by phi, and any set A of possible outputs, the probability that M outputs something in A on input D is at most e to the epsilon times the probability that M outputs something in A on input D prime. Here's the intuition in one sentence. Inputs that phi considers adjacent produce output distributions that are almost indistinguishable. The entire aim of differential privacy is making almost indistinguishable mathematically precise, and that's what this inequality does. Let's unpack the pieces. The first is phi. This is the adjacency relation on inputs, and it captures what counts as neighboring for your application. The classic example is two databases that differ in exactly one row, meaning one has a record for some individual and the other does not. Phi is essentially a parameter, and you can pick it to match whatever notion of privacy you care about. Next is epsilon, which is the privacy budget, and smaller epsilon means stronger privacy. The two distributions have to be closer together. At epsilon equal to 0, applying the inequality in both directions forces the two distributions to coincide, which means that the algorithm reveals nothing about whether the input was D or D prime. As epsilon grows, you get more useful answers, but you get weaker privacy. And choosing epsilon in practice is an engineering problem. And finally, notice that this is a universally quantified definition. The inequality must hold true for all adjacent input pairs and for all output events. And this is a worst-case guarantee. There is no assumption about a potential adversary's prior knowledge and no assumption about what they're trying to learn. And the differential privacy is what we call a probabilistic relational property. The inequality that we just saw doesn't talk about a single run of the algorithm. It relates the output distributions of two different runs on two adjacent inputs. That's the relational part. And it's about distributions, not just sets of possible outputs. And that's a probabilistic part. This is a problem for the kinds of properties we usually verify in TLA+, because in TLA+, we reason about trace properties, properties of individual executions, things like this assertion always holds in every run of the algorithm, or this state is eventually reached. You cannot express a relational property directly within this framework. And we are instead dealing with a hyperproperty, which are properties of sets of executions rather than individual executions. And among hyperproperties, we call those that are defined for pairs of executions relational properties. The classic example for this is non-interference, which says for any two executions of a program that agree on low security inputs for some notion of low security, their low security outputs must also agree. And in the TLA ecosystem specifically, Lamport and Schneider explored how to express and verify hyperproperties, but their approach only handles non-probabilistic ones. Differential privacy is a probabilistic hyperproperty. That is, it's a property defined over sets of executions where the executions themselves are probabilistic, which produces distributions over outputs rather than single outputs. And this puts it outside anything that currently exists in the TLA world, and that's the gap our work is trying to fill. Moving back to DP, or short for differential privacy. A DP algorithm is typically a program which consists of a sequence of deterministic computation interleaved with calls to what we call differentially private mechanisms. There are a few such mechanisms in DP literature. We focus on the Laplace mechanism. It's the most commonly used one, and it's currently the only mechanism our case studies use. And here's how it works. Given a value t, the mechanism releases t plus some noise, where the noise is drawn from a Laplace distribution with scale 1 over epsilon. And the Laplace distribution, it's like the exponential distribution, except it's symmetric and like centered on the input. The privacy guarantee is the following. If on any two adjacent inputs, d and d prime to the program, the values t and t prime that get fed into Laplace differ by at most k, then releasing Laplace epsilon of t is k epsilon differentially private. Take note of what this guarantee depends on. The privacy of a single Laplace call is determined by how the value t fed into it depends on the program's input. And t is computed by the code that runs before the call. The output of Laplace is then used by the code that runs after the call. It can be fed into more mechanism calls, or it can be accumulated into other values, and so on. And all of this affects the privacy of the program as a whole. To reason about this, we first fix a programming language we can express DP programs in, and that's what we'll see next. The language we use is called pvile, due to Barth and colleagues. It's a simple imperative language designed for reasoning about DP programs. The grammar should look familiar. You have standard imperative constructs, skip, sequencing, deterministic assignment, if then else, while loop, and so on, and a return statement. And then there's one extra construct, the probabilistic assignment from the Laplace mechanism. Writing x sampled from Laplace epsilon of e samples a value from the Laplace distribution centered at e and assigns it to x. So, as I said, the language has a standard imperative core with Boolean and integer values, plus probabilistic assignment from the Laplace mechanism. We specifically restrict our attention to programs of the form some code, C, followed by a return statement. Therefore, for us, a program denotes a function, specifically a function from input memories to distributions over output values. And that's a key feature for our semantics, for our purpose, because we want to make the semantics probabilistic by design so that it is possible to state unproved properties like differential privacy directly. Now that we have a language to express differential private programs in, we can talk about how to verify them. And specifically, Barth and colleagues propose a syntactic transformation called the self product that duplicates each variable into two copies and replaces sampling with non-determinism. The goal here is to reduce a probabilistic relational property into a standard safety property of a non-probabilistic program, which can then be proven using ordinary Hoare logic. First, every variable x in the source program becomes two variables, x1 and x2, in the product, one for each of the simulated executions. And secondly, we introduce a ghost variable called v epsilon, which is initialized to 0, and this accumulates the privacy cost along the execution. With that in mind, here are the selected transformation rules. On the left, we have the source program in pvile, which we call C, and on the right, we have the self product, which we annotate C ceiling. Deterministic assignment becomes two assignments, one for each simulated execution using the suffix 1 and suffix 2 variables. A conditional becomes an assertion that the two guards agree on, followed by a single conditional on the suffix 1 guard. And this forces both simulated executions to take the same branch, effectively. And we do something similar for the while loop, where, again, assertions force both executions to iterate in lockstep. And finally, we have the Laplace call. It just gets replaced by what we call an abstract mechanism. That diamond stands for the abstract. So yeah, the Laplace call is replaced by an abstract call to lap diamond. And that's parameterized by the same epsilon and takes in the suffix 1 and suffix 2 versions of the original argument. The semantics of everything we have here, except the Laplace, should be straightforward. And they are normally what you'd expect. Yeah. B1, B2, so B is a variable in the source program, and the self product takes every variable and essentially converts them into two different variables. So B1 is essentially, because differential privacy talks about a relational property, we have two programs. B1 corresponds to B for the first execution, and B2 corresponds to that for the second execution. Yeah. So as for the semantics, Again, like everything besides the Laplace should be obvious. The Laplace diamond non-deterministically picks a value v and then sets both x1 and x2 to that particular value v so that both simulated executions receive the same result. And it adds epsilon times the absolute difference of the two inputs to v epsilon. And yeah, that's the construct. The most interesting thing about this construct is the main theorem that we get out of it. And again, this is not our result, but Barth and colleagues. If we have a program C followed by return out expressed in p-vile, and we have a JSON relation on its inputs we call phi, then if the self product satisfies the Hoare triple with the precondition that D1 and D2 are related by phi, and V epsilon is initially 0, and then in the post condition we have the equality of the outputs, and then we have a bound epsilon on the variable V epsilon, then the original program C return output, again, that's a PY program, that is epsilon differentially private with respect to phi. And just to make clear, D here is the variable that is the program input of the original program. D1 and D2 are the variables that they would correspond to after this self-product construction. Yeah, this is the payoff of the construction. The probabilistic content of differential privacy is entirely hidden in the main theorem proof. And that's done once by Barth and collaborators, and the user does not have to redo it. What's left for the user is a proof of an upper bound on a ghost variable and equality of two variables. That's just the standard safety property of the self-product. And for our work, what we've done is that we adapted Barth's construction to the TLA plus ecosystem. The source language we use is a fragment of Pascal, that is the deterministic fragment of the PY language we presented. And from there, we generate the self-product automatically. Here is the workflow. So the user writes a Pascal algorithm with the Laplace calls expressed as assignments of an uninterpreted operator in the source, and returns our assignments to a special variable called out. And following that, a Python script that we wrote, which uses the tree-sitter grammar for TLA+, rewrites the source into its self-product. And the result is then translated to TLA+ through the standard Pascal translator. And one thing that makes this adaptation natural is that Pascal already has a non-deterministic choice construct called with. And that's what we use to model the abstract Laplace calls in the self-product. The deterministic constructs translate just as in Barth's PY rules expressed in Pascal syntax. Deterministic assignment, that becomes parallel assignment for two variables. For if and while, the role of Barth's assert is played by Pascal's await. Await blocks the simulated execution if its condition fails, which is exactly the semantics we want out of it. So either both simulations agree on the guard or no progress is made at all. The interesting case is the Laplace call. A source code of the form y gets assigned Laplace epsilon of e becomes a Pascal with block. The with non-deterministically picks a tuple res from the set returned by upslap and parallel assigns its components to y1, y2, and the ghost variable v epsilon. Upslap itself, that's an uninterpreted operator from a reusable DP module that we wrote. And for verification, we instantiated to the set of tuples that encodes the Hoare specification of the abstract Laplace call that came from Barth's construction. Specifically, all tuples where the first two components are some value n, and the third component is v epsilon plus epsilon times the absolute difference of the two inputs to the mechanism. That's just the semantics we showed 2 slides ago. After the Pascal translation runs, the self-product becomes a standard TLA specification, and the Hoare triple from Barth and collaborators' main theorem becomes an invariant of that specification. The invariant says when the program counter reach is done, that is when the program has finished executing, the two simulated outputs are equal, and the ghost variable v epsilon is at most epsilon. And this is under the assumption that in the initial state, the two inputs d1 and d2 are phi related, where again, d is the input to the original program. We have 2 ways to check this invariance in the TLA ecosystem. First, TLC, the TLA plus model checker, for which we instantiate epsilon to a concrete unit value and restrict the domain of values to a bounded set of integers. Then TLC can enumerate all reachable states and reports a counterexample if the invariance is ever violated. And this is especially useful if you're trying to catch incorrect privacy budget claims. If you claim a tighter bound than the algorithm actually achieves, TLC can produce a concrete trace witnessing the violation. And the second is TLAPS, the TLA plus proof system, for which we identify an adequately strong inductive invariant that implies the invariant on the slide. And this time we do that for an arbitrary epsilon, not a fixed value as we did for TLC. And then we prove that correct using the standard TLA rule of induction. Moving to our case studies. Our first case study is SmartSum, which is an algorithm due to Chan and colleagues. The goal here is the following. We are given a sequence of integer inputs L1, L2, and so forth. And we release a noisy estimate of every prefix sum. That is the sum of the first k entries for every k. The naive approach here would be to noise every input independently and then accumulating them. But then the errors grow with the prefix length. Whereas SmartSum does something smart, pun intended, by keeping the error bounded by grouping inputs into blocks of size q and then noising the block sums. The input to the program is a sequence of values, and the adjacency relation phi relates two equally long sequences that differ in exactly one position by at most one. And the claim result is that SmartSum is 2 epsilon differentially private with respect to this definition of phi. Here on the left is the Pascal source. It's here for completeness. I don't expect you to follow every line, but the high-level picture is simple. The loop consumes the input list one element at a time. On each iteration, one of the two things happen. In the common case, which is actually the else here, we are not at a block boundary, and as I said, blocks are of size q. Where we are not at a block boundary, we noise the individual element, then add it to an accumulator that collects the running prefix sum. And then at block boundaries, which is the if case here, we noise the entire block sum instead and use that as the new anchor point for subsequent elements. The trick is that each individual element's noises within a block get effectively replaced by a single block sum at the boundary when Q is reached. That's what gives SmartSum its tighter privacy bound. On the right is part of the inductive invariant we identified that we maintain on the self-product. And in fact, it's just the select few of the clauses, the more interesting ones. And the intuition here is the following. The sole different entry between the two input lists passes through 3 different phases as the loop runs. First, it's not yet been processed, so the 2 simulated lists are different, and the privacy cost is 0. Until we reach that entry, we are not consuming any privacy budget. Then it gets read into the accumulator C on one side, but not the other, so C1 and C2 differ by 1. The lists agree from now on, because this was the only differing entry. And then the cost has gone by an epsilon, as we introduced some noise by this differing entry. And then the third case is when the block boundary fires. So we are in the process of processing this different entry. We are then finishing the block that it sits in. And when that happens, the differing accumulator is absorbed into the sum into the noise block sum. And following that, C1 and C2 are set to equal 0 again, so they're equal. And as we introduce some more noise when noising this accumulator, which was differing, we added some more. We used some more privacy budget, and this is in fact at most epsilon. And as we transition between the 2 phases, between the 3 phases, there are 2 transitions, and each of them at most epsilon. That's what gives us 2 epsilon differential privacy. SmartSum was pure epsilon differentially private, but for our second case study, we will need something slightly weaker. Pure epsilon DP is occasionally too strong. Some algorithms can only achieve it at a high cost. So people have introduced this notion of approximate differential privacy, sometimes written epsilon delta differential privacy, which relaxes the definition with a small additive failure property delta, you can see on the right. And the inequality that you end up with is almost identical as before. Intuitively, with probability at almost delta, this privacy guarantee that we have is allowed to fail with this modification. Barth and colleagues then extend the self-product framework to handle approximate differential privacy by introducing a second ghost variable that they call v delta, which is also accumulated along the execution. And then the main extended theorem says if the self-product satisfies the Hoare triple with the precondition that has v epsilon and v delta both initialized to 0, and again, the inputs are related by phi, And then in the post condition, if you have that both outputs are equal, as before, the epsilon bounded as before, plus v delta now being bounded by some parameter delta, then the claim is that the original program C return out is epsilon delta differentially private with respect to phi. I'll for now skip how this extension changes the self-product construction semantic itself. I will only discuss how it relates to how it shows up in our framework. Our framework actually already supports reasoning about v delta. I just hit that earlier in the presentation to keep things simpler. And in our framework, what really happens is the user picks which specification of the Laplace mechanism is to be applied at each Laplace call in the proof. There are two of them. The first is the standard specification, the same one as we've already seen. Laplace call costs epsilon times the absolute difference of the two simulated inputs, and v delta is left untouched. The second is the accuracy specification, which requires that the two simulated inputs to the Laplace call are equal. That's the precondition. And then it makes a different trade. It doesn't change anything in the epsilon budget. What it now does is it does charge the delta budget. And it also constrains the output value to not be an arbitrary value, but to a particular value that is within a distance t of the input for some parameter t, which is part of the spec definition. The amount it charges to v delta is called lap tail of epsilon and t. Lap tail is the standard tail bound for the discrete Laplace distribution. Mathematically, it's equal to 2 times epsilon e to the epsilon t. 2 times e to the minus epsilon t. There you go. It's the probability that a Laplace sample lands more than TLA from its center. So intuitively, the accuracy specification says if you don't want to spend epsilon budget, you can instead constrain the output to be close to the input. And then the cost of that constraint is the probability that it fails, which is lap tail. Our second case study is the proposed test release algorithm, or PTR, which is due to Dwork and Lay. The setup is the following. We have queries, which are functions from a database domain to some space of query outputs. And we assume a distance metric on the database domain, a function from pairs of databases to natural numbers that satisfy the standard metric axioms. And the key concept of this case study is the distance to instability, which I'll abbreviate DTI. DTI of a query Q and a database D is the largest radius R such that the query gives the same answer on every database D prime within distance R of D. Intuitively, it's the size of the stable neighborhood around D. It's how far you can move from D before the query answer changes. And by definition, DTI is one sensitive. If you move from D1 to a database D2 within distance 1, then the value of DTI changes by at most 1. Now for the algorithm itself, which is somewhat simpler, given a fixed query Q and a threshold parameter T, what PTR does is releasing the true query answer to Q of D only when D appears far enough from instability. The code is as follows. First, we compute X, the DTI for our database D. Then we add Laplace noise to X and getting a noisy estimate Y. Afterwards, we run a test. If the absolute value of Y is greater than X, then we return the true query answer. Otherwise, we release a fixed dummy query output value. The intuition is that if X is large, then the database is stable. Its query answer won't change under small perturbations, so it's safe to release. And the noise between the noise plus the threshold protects us from leaking information about X itself. So that's the role of Y. The adjacency relation phi is the most natural one. It's 2 databases at distance at most 1. And the result is that PTR is epsilon and lap tail of epsilon and t differentially private with respect to phi. That is an approximate DP algorithm whose delta budget is the Laplace tail bound for epsilon and delta parameters. So I'll give a proof sketch here. The privacy proof is working by case splitting on whether the 2 simulated databases agree on the query or not. So meaning whether they return the same result for the query. Also remember that the input to the Laplace call is DTI of QD, which is 1 sensitive. In the first case, when the queries agree on the 2 databases, the standard Laplace specification is enough. and both branches of the if release the same value, either the agreed query answer or dummy on both sides, and the only cost we pay is at most epsilon on the epsilon budget, since the inputs to the Laplace call, which are the DTI values, they differ by at most 1. In the other case, when the queries disagree, we have that the DTI values are both 0 since the databases are adjacent. The accuracy spec is then what we use, and that constrains the noisy answer y to lie within distance t of the input on both sides. Therefore, both runs end up releasing the dummy by failing the guard on the if then else. The cost we pay this time is on the delta side, and as we said, that's equal to the Laplace tail. The remark to make here is that both specifications get used in the same proof of the Laplace call under different assumptions about the simulated inputs. That's what makes PDR an interesting case study, we thought. And that wraps up the second case study. Now I share a few limitations of our work before I close. The first is the limited support for real arithmetic in TLA plus and TLAPS. Privacy parameters like epsilon, they are real valued, and expressions like lap tail of epsilon t, which is mathematically just 2 times epsilon, 2 times e to the minus epsilon t, and that's simply not definable in TLA plus right now. And we work around this by treating that as an uninterpreted operator, and anytime we reason about reals, we simply isolate trivial real arithmetic facts, and we admit them as assumptions. The second limitation is breadth. Besides Laplace, we have the definitions in place for something that's called the exponential mechanism, but we haven't finished the case studies using it yet. And we could always explore other mechanisms from the DP literature. And the last one is about model checking with alternating specifications. TLC, the model checker, you cannot instantiate a constant operator with multiple possible definitions and then do parallel runs on that. Well, whereas PTR, our second case study, relies on alternating the Hoare and the accuracy specifications of the Laplace mechanism at different points in the proof. That's fine because in TLAPS we can simply resort to different assumptions in different parts of the proof. But it is a roadblock in model checking the specification. It seems like a unified spec definition that kind of subsumes both definitions is feasible, but we haven't fully explored this yet and not implemented it. To wrap up, our contribution is a framework for verifying differential privacy of programs expressed in a fragment of Pascal by adapting and automating Barth and colleagues' self-product construction to the TLA ecosystem. And to the best of our knowledge, this is the first verification of a probabilistic hyperproperty in TLA. And for future work, we are interested in 2 directions in particular. The first is differential privacy in concurrent settings. TLA is a natural place to model concurrent and distributed systems, and we'd like to leverage that to reason about DP algorithms that are themselves concurrent or distributed. And secondly, we would like to explore broader product constructions for the verification of probabilistic hyperproperties. One example that we're currently looking at is memory trace obliviousness for ORM-like constructions. If you're interested in this work, the abstract is available at that link, and please feel free to reach out. Thank you.